Good morning. Today we are going to continue with our chapter complex numbers. In the previous class we had discussed with addition of complex numbers, which says that addition means that if we are given two complex numbers z1 equal to a1 plus ib1 and z2 equal to a2 plus ib2, then z1 plus z2 is another complex number having the real part as the sum of the two real parts and the imaginary part as the sum of the two imaginary parts. And it's also so this is a complex number. Same way, if you consider subtraction, then subtraction of two complex number also is another complex number having the real part as the difference of the two real parts and the imaginary part as the difference of the two imaginary parts. Okay, so both addition and subtraction are themselves complex numbers. Like for example, if we are given z1 is equal to, let's say, 3 plus 5i and z2 equal to minus 2 plus 7i. So z1 plus z2 would be sum of the two real parts, that is 3 minus 2 plus I times sum of the two imaginary parts, which is 5 plus 7, which is equal to 1 plus 12i, which is also a complex number. Same way, if you do the subtraction, z1 minus z2 would be difference of the two real parts, that is 3 minus of minus 2 plus I times difference of the two imaginary parts, which is 5 and 7. So 5 minus 7, which gives us 3 plus 2, that is 5 plus, now here we have minus 2 I, which is also a complex number. Now let us proceed to do the next operation, that is multiplication of complex numbers. Now again we start with the same two complex numbers z1 and z2, and let's see what is the product of the two complex numbers. So we'll write it as a1 plus ib1 into a2 plus ib2, and we open it of the two product terms the same way as we have been doing in product of two linear functions, where treating I in place of x. So the same way we open it up, a1 into a2 plus a1 into ib2 plus ib1 into a2 plus ib1 into ib2. Now this comes out to be a1 a2 plus I times a1 b2 plus I times b1 a2 plus I square times b1 b2, but I square equal to minus 1. So we get z1 into z2 is equal to a1 a2 plus I times a1 b2 plus I times b1 a2 minus b1 b2. Collecting the real and imaginary parts, we get z1 into z2 is equal to a1 a2 minus b1 b2 plus I times a1 b2 plus b1 a2. Clearly a1 a2 minus b1 b2, it's the difference of the product of real numbers, which is a real number. Same way here also it's a sum of the product of real numbers, so this is also a real number, and so z1 plus cross z2 is another complex number. So hence we have seen that multiplication of complex numbers is also a complex number having the real part as the difference of the product of the two real parts and the two imaginary parts, and the imaginary part as a sum of the product of one real with the other imaginary and other real with the first imaginary. So, this is the thing. So, we have seen that multiplication of complex numbers is also another complex number. Now, just like addition, multiplication satisfies closure property. Closure because product of two complex numbers is another complex number. So, we call it closure property. Now, it is also commutative in nature. Commutative means Z1 Z2 equal to Z2 into Z1. Then identity exists. Identity exists means when the product of a number with any complex number gives you back the same complex number. So, identity exists and is equal to 1 plus 0i, the same way which is equal to 1 actually, which is the same in case of real numbers. So, in case of real numbers, if you multiply any number with 1, you get back the same real number. Now, instead of 1, we can always write 1 as 1 plus 0i. So, in case of complex numbers, the identity element is 1 plus 0i, which when multiplied to any complex number gives us back the same complex number, as we can check it just now. So, let us take 1 plus 0i into a plus ib will give us the difference of the real number, product of real numbers and imaginary numbers, plus I times one real and the other imaginary number plus the other real and the first imaginary number, which gives us a plus ib, which is the same number as we started with. And so, it implies that 1 plus 0i is the multiplicative identity. Okay. Now, we come to multiplicative inverse. Multiplicative inverse. Now, multiplicative inverse means is a complex number which when multiplied to another complex number gives you back the multiplicative identity. So, let Z2 or let Z2 be the multiplicative inverse of Z equal to Z1 equal to a plus I b. So, it implies that Z1 into Z2 should be equal to the multiplicative identity, that is 1 plus 0i, which is equal to 1. Now, what we do is it implies that Z2 equal to 1 upon Z1, which is 1 upon a plus ib. We need to solve this. Now, we claim that the multiplicative inverse is also another complex number. So, we have to see how. Okay. Now, as you have already studied earlier that we never leave a square root or an irrational number in the denominator. So, we rationalize the denominator by multiplying and dividing by the same irrational number. Same way, we never leave a complex number in the denominator, or basically we never leave a I term in the denominator, we need to remove it by, so we call it rationalizing the denominator. So, rationalizing the denominator we get. And how do we rationalize it? We multiply and divide by a minus ib. Okay. So, what we get is Z2 will be 1 over a plus ib into, so what we do is we change the sign of the imaginary part and multiply and divide by that. So what we get is a minus ib upon a minus ib. This gives us 1 into anything is the same, that is a minus ib upon. Now it's of the form x plus y into x minus y. So x square minus y square. So you get a square minus ib whole square. So z2 is equal to a minus ib upon a minus ib upon a square minus I square b square, which is a minus ib upon a square. Now I square is minus 1, so this becomes plus b square. It is equal to a over a square plus b square minus I times b, or you can write plus I times minus b over a square plus b square. This is the multiplicative inverse of a plus ib. You don't have to mug up this result, simply do the procedure and get this. So to start with, let us do some questions, that is, find the multiplicative inverse of first number, let's say 2 plus 3i, second number minus 2 or minus 3 plus 7i, third number minus 1 minus 6i, and fourth number, let's take it as 8 minus 3 or 8 minus 9i. So just try out these questions and then we'll proceed further later. Thank you.